It is like it's a universally relatable frustration at this point. You're working with an AI assistant and you've been collaborating with it for, I don't know, weeks, maybe even months.
Oh, yeah, absolutely.
And you feel like it finally gets you right. Like it understands the nuances of your project, your formatting preferences, even your weird little inside jokes.
It's dialed in.
Exactly. It's dialed in. And then suddenly you ask it a question that requires it to, I don't know, connect a dot from today to a dot from like 3 weeks ago, and
Blank stare.
blank stare.
Yeah.
Yes, it completely drops a crucial detail or just totally fails to connect the dots from a past conversation. You're just left feeling like you have to start all over again.
Right. So frustrating.
Have you ever experienced that? Because today's deep dive is about to solve that exact problem.
Yeah, and I mean, it is arguably the most significant bottleneck in artificial intelligence right now.
For sure.
As AI transitions away from just being, a simple single-turn question and answer bot
Hmm.
and moves toward long-term multi-agent collaboration, memory is no longer just a neat feature.
Right. It's essential.
It's the core capability. It dictates whether these systems actually work in the real world at all.
Okay, let's unpack this because we have a really fascinating state-of-the-art paper grounding our discussion today.
We do.
It's titled SAGE, a self-evolving agentic graph memory engine for structure-aware associative memory. That is a mouthful.
It really is a mouthful, yeah.
But our goal today isn't just to talk about how AI stores data on a server. We're talking about how researchers are trying to give AI a dynamic, self-improving, almost human-like memory structure.
And what's fascinating here is that the researchers explicitly state that memory is to long-horizon agents what parameters are to foundation models.
Oh, wow. Okay.
Yeah, it's that fundamental. If an AI cannot accumulate, organize, invoke, and constantly update its memory over long time scales, well, it can never achieve true personalized adaptation.
It just resets.
Exactly. It will always just be a goldfish basically resetting every time you clear the chat.
So to appreciate what SAGE is actually doing here, we should probably look at why current memory fails so spectacularly.
Right. Let's look at the baseline.
Because if you're using a modern AI, the system working behind the scenes is usually standard arg, right? Or retrieval augmented generation.
Yep, standard arg.
And to me, standard arg feels like an incredibly messy filing cabinet. Like you ask a question and the system just frantically opens drawers and grabs independent text chunks that have matching keywords.
Just throwing them on your desk.
Yeah, or just tossing them everywhere. It doesn't know how the chunks relate to each other. It just knows they both contain the word like marketing or budget.
And that fragmentation is the absolute root of the issue. Because RAG retrieves independent fragments.
Yeah.
But long-term agent memory usually requires recovering a whole chain of evidence that is, distributed across entirely different entities, different events, multi-hop dependencies.
It's not just one document.
No, definitely not. And to fix this, the industry recently took a step forward with something called GraphRag.
Okay, right. GraphRag.
GraphRag takes all those loose documents and entities and organizes them into a structured graph. So it makes the cross-document dependencies much more explicit.
Right. So instead of a messy filing cabinet filled with loose paper, GraphRag is like a map. It actually draws the physical roads between the cities.
Exactly. A perfect analogy.
But wait, I'm stuck on one thing, though. If GraphRag already connects the dots on a map, why isn't that enough for long-term reasoning? Like, if it already draws the lines, why are we still getting lost?
You would think it's enough, right? But the problem lies in how that map is actually used.
Okay.
In existing systems, the graph is treated as what researchers call static retrieval middleware.
Static middleware.
Yeah. It is essentially a physical map that you print out, laminate, and consult after the fact.
Ah, I see.
But for a long-horizon agent, something that's supposed to live and learn alongside you over months.
It can't just be a fixed PDF.
Exactly. A graph cannot just be a static PDF you search. It needs to be a dynamic working substrate.
Or working substrate, meaning the map has to actually be alive, right? Like updating while you're driving.
Yes, and this introduces the core concept of SAGE. SAGE proposes an architecture where the memory graph is continuously written, read-corrected, and self-improved purely through its interactions with you.
Oh, that's cool.
The graph isn't just an index built before retrieval. It is the medium through which the AI actually studies its own retrieval failures.
Okay, so if the graph needs to be alive, the paper points out 3 major hurdles to making this a reality, right?
It does, yeah.
And the first hurdle is actually just finding things in it when humans give terrible, vague instructions.
Oh, we always do.
We do. The paper calls this global associative reading from fragmented cues, which is essentially dealing with the tip of the tongue phenomenon.
We do this to our AI assistants constantly. When you interact with a long-term agent, your queries are almost never perfectly phrased database searches.
No, never.
You might only drop like an episodic clue, an alias, or a really distant conceptual hint. The answer you actually want depends on intermediate steps that you just didn't explicitly name.
Right, and the paper has this wild, highly specific example to illustrate this. Let me translate it a bit because the raw prompt in the paper is super dense.
Yeah, it's very academic.
So imagine asking your AI, hey, remember that biology term Alice brought up in last week's lab meeting? Cornu something. Is there an AI memory paper inspired by something in that same biological field?
That's a brutal prompt.
Right. If you ask a standard AI that it's going to completely short circuit, look at how sparse those explicit cues are, right? Okay. Alice meeting a partial biology term and AI memory.
Yeah, our Methy filing cabinet is going to find the meeting notes about Alice, maybe.
Maybe.
And it might find a biology textbook about the cornu ammonis, which is, part of the hippocampus, but it won't be able to connect them.
Because there's no direct keyword link.
Exactly. It won't connect them because standard vector retrieval requires direct semantic overlap. It cannot form a complete reasoning chain from those fragmented cues to the actual answer, which in this case is the SAGE paper itself.
SAGE is inspired by the hippocampus, right?
Yes. And this is where cognitive science enters the architecture. SAGE solves this by using a graph foundation model, or GFM, as its memory reader.
Okay, wait, before we lose the audience on the jargon, what actually is a graph foundation model? How is it different from just a normal language model?
Well, a standard language model is trained to predict the next word in a sequence of text, right?
Right, like autocomplete.
Yes. But a graph foundation model is pre-trained on massive knowledge graphs to natively understand structural topologies.
Structural topologies.
Yeah, it isn't just reading strings of text. It is trained to predict the next logical node in a web of ideas. And to do this with vague prompts, it uses a mechanism called soft addressing.
Soft addressing. What does that actually look like physically in the system?
Normally, computers use hard addressing. You tell it to look in folder A file B.
Right, the exact coordinates.
But human brains use semantic priming. When you try to remember a movie title, you don't search an alphabetical database in your head, right?
No, I just think of like the lead actor or the color of the poster.
Exactly. You think about the feeling of the theater, the poster. You generate multidimensional retrieval cues that awaken peripherally related memories.
Okay.
Soft addressing mathematically simulates this. SAGE takes your vague natural language query, decomposes it, and assigns probability weights like little packets of energy to various starting nodes in the graph.
Rather than demanding an exact street address.
Exactly.
So it's like throwing a pebble into a pond, right? SAGE isn't just staring at the exact spot the pebble hit the water, it is sensing the ripples moving outward to activate related memories.
That's a great way to look at it.
But wait a second. If you throw a pebble into a pond, the ripples go outward uniformly in like every direction. If SAGE is awakening all these peripheral memories, couldn't it just get completely flooded by irrelevant, noisy data?
And that brings us directly to challenge 2, navigating structural information. Because you're right, the graph structure shouldn't be expanded uniformly or blindly. SAGE has to learn how different structural roles affect the flow of information.
Okay, structural roles. Give me a concrete example of what you mean there.
Let's trace the path in that Alice example.
Okay.
As SAGE ripples outward from the biological term cornu ammonis to the hippocampus, it eventually hits an AI paper called hipparag.
Right, hipparag.
In the geometry of this graph, hipparag acts as a bridge. It is a vital, narrow path connecting a biology concept to an AI memory concept.
Okay, I see.
But as the energy continues to propagate outward, it's eventually going to hit terms like graph rag, or just rag. And in AI literature, those terms are massive, highly connected hubs.
Ah, I see. So it's recognizing that the massive highway interchange, the hub is going to be jammed with millions of completely irrelevant papers. So to get to the actual answer, it forces the GPS to take the suspension bridge, the narrow back road.
That is the perfect way to visualize it. Traditional methods often use heuristic expansion, meaning they just blindly spread out to all connected nodes evenly, and they end up stuck in that highway traffic.
In the hubs.
Yeah. SAGE, however, uses what the paper calls synapse-inspired, structurally conditioned associative propagation.
Another massive term.
I know, but it just biologically mimics how human brain synapses fire.
Meaning it can actively control the traffic based on the shape of the road.
Yes. It performs inhibition where it actively suppresses the energy flowing into those noisy, generalized hub edges like R and J so it doesn't get flooded.
Oh, nice.
Simultaneously, it preserves lateral thinking, deliberately saving the energy for long-distance bridge edges like Hipparag
Yeah.
to cross into different cognitive clusters.
To make those weird intuitive leaps.
Exactly. And finally, it undergoes habituation, weakening the connections to redundant local information so it doesn't just get trapped reading the same meeting notes about Alice over and over again.
I love that. But I'm still trying to figure out how the AI actually learns the rules of this specific road.
Right.
Because, as we established earlier, this isn't a static map we printed out. If I'm using this AI every single day, I am constantly adding new projects, new concepts, new inside jokes.
The terrain is shifting.
Yeah, the map is changing daily. How does it know what a hub or a bridge is if the road is literally still being paved?
This is the absolute heart of the SAGE system. Challenge 3, the closed loop, the self-evolving memory.
Okay.
Most existing methods assume the knowledge graph is already built and finished and they just optimize the search algorithm. But for a true long-term agent writing, the memory is just as critical as reading it. SAGE actually splits its architecture into two distinct roles.
The memory writer and the memory reader.
Yep. The writer is the entity incrementally constructing and updating the graph from your interaction history. It extracts entities and relationships from your chats and mathematically fuses them into the existing web.
So it's the one out there paving the roads.
It is. And the reader is the GFM we just talked about, the one driving on the roads performing the associative retrieval. But here is the critical innovation. The reader provides direct reinforcement feedback to the writer.
Okay, let's slow down here. How does that feedback actually change the writer's behavior? How is it trained to pave better roads?
The writer is trained using a specific type of reinforcement learning called clipped GRPO, which stands for Group Relative Policy Optimization.
Okay.
Instead of just giving the AI a binary pass or fail, the system generates a batch of different possible graph updates. It scores them relative to each other based on how useful they were to the reader, and then rewards the policy that performed best.
And the clipped part.
The clipped part just means it prevents the AI from making massive erratic changes to its brain all at once based on a single reward.
Oh, okay, so it doesn't overreact.
Right. But the real secret sauce is what it rewards. The paper highlights a vital distinction between a recall reward and a deducible reward.
Let me guess. If you only give it points for recall, meaning you reward the writer just for making sure the correct text chink is somewhere in the graph, it's going to cheat right.
Oh, totally.
Like a lazy student who just highlights the entire textbook instead of figuring out the important concepts.
The lazy student analogy is spot on. If you only use a recall reward, the writer becomes incredibly noisy. It just writes down everything, inflating the graph with massive amounts of weakly related evidence, hoping the reader will stumble upon it.
Right.
It doesn't build a reasoning chain, it just builds a bigger pile of garbage.
Which totally defeats the whole purpose of having a map in the first place.
Exactly. So SAGE relies heavily on a deducible reward. This reward measures whether the graph structure can actually support the step-by-step derivation of the answer.
Ah, so it has to prove its work.
Yes. It forces the writer to build clean evidence chains and properly connect those bridging entities we discussed earlier, ensuring the reader can genuinely reason its way to the solution.
Here's where it gets really interesting to me. It sounds like the AI is essentially studying its own retrieval failures to reorganize its internal brain.
If we connect this to the bigger picture, that is the definition of self-evolution in this context, better reading exposes writing deficiencies.
Wow.
If the reader keeps failing to get from point A to point C because point B is missing, the reinforcement learning signal tells the writer, hey, you need to build a bridge here.
Because I'm getting stuck.
Right. And consequently, because the writer builds that bridge, future reading becomes much more selective and accurate. It is a continuous self-improving loop.
Okay, I have to play devil's advocate for a second.
Sure.
If the writer is constantly changing the graph, paving new roads, tearing down old ones, building bridges based on daily interactions, how does the reader not get completely disoriented?
That's a great question.
Right, because if the terrain of my memory is shifting every single day,
Right.
how does the AI maintain any kind of stable reading comprehension?
The researchers actually anticipated that exact instability, and they solve it using a mechanism called context schema decomposition.
Okay, what is that?
Well, you're entirely correct that the reader cannot rely solely on the propagation patterns of a fixed graph, because the graph is never fixed. So it separates its understanding into two distinct channels.
How does it separate them?
First is the schema channel. This represents the AI's transferable long-term reading habits. Think of it as the foundational understanding of how information is naturally structured.
Like the fundamental physics of the map.
Exactly. Its ability to recognize the abstract concept of a bridge or a hub across any graph. It relies on the cognitive priors formed during the GFM's pre-training.
I see. So the schema is like knowing how to read a map in general. You know that blue means water and thick lines mean highways, regardless of whether you're looking at a map of New York or Tokyo.
That's it. And then the second channel is the context channel. This is the immediate lightweight calibration to the specific messy target graph that the writer just updated. It captures the immediate structural state of your current memory web.
So if the schema is general map literacy, the context channel is figuring out that in this specific city, Main Street is suddenly closed for construction today, so we need a detour.
Perfectly said. And by combining these two, the reader adapts to the current terrain while preserving its cross-graph structural prior.
That's so smart.
The paper actually proves mathematically in Proposition 1 that this decomposition leads to evolution stability. It guarantees that even though the writer is continuously shifting the distribution of information, the reader's output doesn't oscillate wildly. The system remains stable as it learns.
Okay, so we have this incredibly elegant, neurologically inspired architecture. We have a writer and a reader locked in a loop of self-improvement balancing long-term schema with short-term context and mimicking human synapses to avoid traffic jams.
Yep.
It sounds brilliant in theory, but what do the actual benchmarks say?
The numbers are incredibly robust.
Yeah.
SAGE was tested extensively across multi-hop question answering datasets like Hotpot QA Music and 2Wiki Multi-Hop QA.
Hey.
After just 2 rounds of self-evolution, it achieved the best average rank across these benchmarks, decisively beating out highly specialized static systems.
Wow. And what about open domain transfer? Like, can it handle topics it wasn't explicitly trained on, or does it just fall apart?
In zero-shot open domain transfer on the natural questions dataset, it hit a massive 82.5 recall at 2.
What does that mean exactly?
That means even without seeing the specific training data for that domain, its underlying structural reading habits, that schema channel we talked about, allowed it to find the exact right evidence within its top 2 guesses over 82% of the time.
That is wild. And how fast is this process? Because frankly, nobody wants to wait 5 minutes for their AI assistant to remember what they talked about last week while it calculates all these synaptic pathways.
The retrieval time is a blazing fast 0.032 seconds.
Wait, 0.03 seconds.
Yes. To put that in perspective, some iterative retrieval methods that try to do similar multi-hop reasoning by constantly querying an LLM can take over 2 or 3 seconds per hop. SAGE is magnitudes faster because it isn't wildly guessing. It is using its structural schema to shoot straight down the correct associative bridges.
Okay, those numbers sound great in a computer science lab on clean data sets, but what does this mean for you, the listener? If you're a project manager or an engineer and you just want a better AI assistant that actually remembers your chaotic life, how does this translate to the real world?
The researchers tested exactly that practical application. They evaluated SAGE on Amazon QA, which is a real-world e-commerce dataset full of noisy, contradictory, grammatically incorrect product reviews.
So the messy stuff.
Exactly. And SAGE consistently outperformed the baseline models, proving it can parse the messiness of real human data. But even more crucially for everyday users, they tested it on LongMemeMul and Hallamem.
What are those testing for specifically?
They are benchmarks designed to evaluate long-term agent memory. They test multi-session reasoning, like can the AI remember a passing detail from a chat 3 weeks ago and apply it to a problem today? They test temporal constraints. Does the AI understand the actual sequence of events in your workflow? And they test operation-level hallucinations.
Which is when the AI confidently makes up a fake fact just because it forgot the real one and wants to please you, right?
Exactly. And the results suggest that SAGE's reader-writer feedback loop significantly improves hallucination diagnostic metrics.
Because of that deducible reward.
Yes, by forcing the writer to focus on answer deducibility rather than just keyword recall. The AI is much less likely to invent facts to bridge a gap in its memory. It actually learns to construct valid, traceable evidence chains based entirely on your long-term interaction history.
So what does this all mean? To summarize our journey today, for a long time, we've treated AI memory like a static, dusty warehouse.
Yep.
We throw text chunks into a filing cabinet, and when we need something, we just hope the search algorithm grabs the right piece of paper.
Yeah.
Even when we upgraded to GraphRag, we were still just drawing a static map of that warehouse.
Exactly.
But SAGE completely changes the paradigm. It turns AI memory into a living, self-evolving ecosystem. You have a memory writer actively extracting entities, paving roads, and building bridges based on your
A
conversations.
living map.
Yeah, you have a memory reader navigating those roads, using human-like semantic priming to catch your vague cues, actively inhibiting the noisy hubs to avoid traffic, and using reinforcement learning to tell the writer exactly where the infrastructure needs to improve.
It is a profound shift from viewing memory as a cold storage device to viewing memory as an active cognitive process.
It really is.
And it leaves us with a fascinating implication to consider.
Oh, yeah.
If an AI's memory structure is constantly rewiring itself based on your specific interactions, if it is actively reinforcing bridges and suppressing hubs based solely on the unique, chaotic data of your life, your projects, and your strange questions, at what point does its internal graph of your history become entirely unique?
Well,
Right. We might be looking at a future where your personal AI assistant develops a cognitive architecture that no other AI and perhaps no human could ever replicate simply because its brain evolved exclusively around you.
that is a wild thought to mull over the next time your current AI forgets what you told it 5 minutes ago. Think about how you organize your own memory and imagine a system that learns to do it just like you. Thanks for joining us on this deep dive into the Sage architecture. We'll catch you next time.